All right, the next electrophilic aromatic substitution reaction that we're going to look at is called the Friedel-Crafts Alkylation reaction. So again, let's look at the overall reaction before we jump into the mechanism. So the overall reaction, again, involves an aromatic ring as your starting material. In this case, I'm just going to use benzene. And then what we're going to have is some sort of alkyl halide. So really what this R group is right here is it's going to be some sort of alkane. Okay, so we've got some sort of alkane with a halogen coming off of it, and we're going to again use a Lewis acid catalyst like aluminum trichloride. When this reaction occurs, what you can do is install that alkane immediately onto the aromatic ring. So it's a good way of creating a new carbon-carbon bond. All right, so let's take a look at the mechanism here. The mechanism is pretty straightforward, but there's a few things you have to watch out for, so let's be careful. First things first, I'm just going to make up some sort of group. So I've got tert-butyl chloride here as my halogenated alkane. So like I said before, this group really has to be an alkane, meaning that this central carbon here must be sp3 hybridized. We'll talk more about that later. All right, so we've got this in solution. This has lone pairs, and we also have our acid catalyst, which is our aluminum trichloride. And if you remember from our previous lecture video, this aluminum is sp2 hybridized, so it's sp2. It means that this has an empty p orbital. Because it has an empty p orbital, it's a really good Lewis acid. It wants electrons in one of the p orbital lobes, and in this case, the chlorine has electrons that can be donated to that empty p orbital. All right, so let's take a look at the next intermediate. So we've got the chlorine now bonded to the aluminum. The aluminum is actually going to change hybridization from sp2 all the way to sp3 and therefore become tetrahedral. So we've got this intermediate now, and this intermediate is really unstable primarily due to the fact that chlorine does not want that positive charge. So this will fall apart and quickly kick off chlorine. All right, when we do this, we're going to create a carbocation, and then we've got our aluminum group that was kicked off. So this carbocation is really, really reactive. However, there's one important thing students always forget about, and that is you have to watch out for rearrangements. Just like we saw earlier on this year, carbocations will rearrange if they can form a more stable carbocation. In this case, there's not going to be any carbocation rearrangements because there's not a better carbocation that could be formed with this system. So remember, resonance is best, followed by tertiary, followed by secondary, followed by primary. So we do have to watch out for these carbocation rearrangements. All right, but in this case, like I said, we don't have to worry about that. So what we'll do next is we'll react this with our aromatic ring. In this case, the carbocation is a really good electrophile. It desperately wants electrons, and in this case, the aromatic ring can actually dump electron density in from one of those pi bonds. So what we're going to get is something that looks like this, where we've got a tert-butyl group installed. We'll have a positive charge over here, and then we'll still have this aluminum complex floating around in solution, which is going to help us out in this next step. All right, so we've got this aluminum floating around in solution. We've got this sigma complex right here. We know that the sigma complex is really unstable because we've broken aromaticity. So what we're going to do is we're going to use one of these chlorine atoms as a really weak base. So this entire chlorine atom, along with the electrons from that bond, are going to act as a base, And so I show that arrow coming from that bond to this hydrogen, and then we can clamp down and restore aromaticity. So when we do this, we're able to install that tert-butyl group, and we're also going to regenerate this aluminum trichloride catalyst, and the byproduct in this reaction is going to be HCl, meaning the conjugate acid from that previous reaction. All right, so this reaction is pretty neat. It's pretty useful. Another cool thing is that you can do this with alcohols. So let's take a look at another example. And let's say we do this reaction with benzene, and we use tert-butanol, and we use H2SO4 that's concentrated. Well, what do you think will happen? Well, we could protonate this alcohol here, right? At which point it would be a good leaving group. It could fall off, give us the same carbocation, and this reaction could work. So this reaction also works with alcohols, which is kind of neat. The key feature of this reaction is you have to have some sort of carbocation to act as your electrophile, because benzene itself isn't a very good nucleophile. The only way to get around a weak nucleophile is to have a super strong electrophile. All right, so let's practice a little bit. And I'll show you a few situations that we need to be aware of. So let's try this example. So I'm going to have benzene, and I'm going to add in 1 chloropropane as my aromatic halogenated hydrocarbon, and I've got aluminum trichloride as my catalyst. My question is, well, what products could we get out of this reaction? Well, a lot of students will just really quickly say, well, this whole group is going to get installed on the aromatic ring. So wouldn't our product just look like that? Well, the answer is not really. Actually, if you do this reaction, you only get about 35% of that product. The reality is this could quickly rearrange, because if this whole group were to fall off, right, we'd have a primary carbocation on this carbon. That doesn't want to happen. It'll quickly rearrange and give us a secondary carbocation. So see if you can practice that at home. Make sure you're comfortable drawing carbocation rearrangements. But the major product you'll get out would be isobutylbenzene, and you get that at about 65%. So you can see the rearrangement is something you really need to be aware of. So let's take a look at another example. In this next example, I'm going to use chloroethane and aluminum trichloride, just like before. And some students will say, whoa, that's a primary carbon. Won't this rearrange too? Well, not exactly, right? If that chlorine were to fall off, you get a primary carbocation. Yeah, that's unstable, but it can't rearrange into anything better. So in this example, you'll still get this product because there's no chance that rearrangement will occur. All right. So now what I want to do is I want to quickly look at some of the problems with Friedel-Crafts alkylation, because there are a few things that we need to be aware of. All right, so let's make a list of some of the limitations for these. So number one, we already covered, and that is that alkyl halides can rearrange. It's something we need to watch out for. However, it doesn't occur all the time. So for example, it doesn't occur with an ethyl group. Like we saw in that last example, ethyl groups can't rearrange into anything more stable, or methyl groups. So those ones we don't need to worry about, but other ones, specifically primary ones, we do need to watch out for. Number two is one that I mentioned already, and that is that it only works with sp3 hybridized alkyl halides. All right, so I'll show you an example of one that will not work. So some students will say, well, let's say I want to do this reaction in an attempt to make styrene, right? So some students will say, well, won't this group get installed? Not exactly. The main problem with this is that this is sp2, and because the chlorine is coming off of an sp2 carbon, we are going to get no reaction. This reaction will fail 100% of the time. All right, the third one gets a little bit more complicated, and we'll talk more about this later, but it is that alkyl groups are what we call activating groups. Activating essentially means that once you install one, this following reaction is actually even faster, which means that this leads to over-alkylation, an uncontrollable reaction. So really, it's kind of this problem where it's really hard to stop at just installing one group. Usually, it'll keep on going. So I'll show you an example of this. So let's say we've got this tert-butyl chloride and aluminum trichloride. What will happen is we'll get that tert-butyl group installed once. However, this is actually more nucleophilic than this. This one is less nucleophilic. The reason it's more nucleophilic is this group actually contributes some electron density to the aromatic ring, therefore making it a slightly better nucleophile, which means that this next reaction, assuming you have any starting material floating around in solution, will occur really, really quickly. Specifically, it will result in ortho or para substitution. In this case, it's going to prefer getting para substituted. Again, we'll talk about this a lot more later. All right, there's one last thing we need to talk about, and that's one major pitfall with this reaction. This has to do with strongly deactivated rings. So strongly deactivated rings simply won't do this reaction. So strongly deactivated aromatic rings cannot do a Friedel-Crafts reaction. So I'll show you what I mean by that. Over here, I've got nitrobenzene, which we saw we can make from benzene using concentrated nitric acid and sulfuric acid. But the main issue with this is that we've got a resonance structure where we can actually pull density out of the aromatic ring. That means that this is an electron withdrawing group, which means that the aromatic ring is really, really poor. All right, because it's such an electron withdrawing group, it actually hinders this reaction to the point where it doesn't readily occur. So if we were to try to do this same reaction, nothing would happen. So we have to make sure that when we're doing a Friedel-Crafts reaction that we do not have an electron withdrawing group that's really strong off of the aromatic ring. It's okay to have a moderate electron withdrawing group, but you can't have a really strong electron withdrawing group. Again, we'll talk about how to differentiate between those in a subsequent lecture. All right, good luck.